All right, here we are. This might be the very first time I've made a PowerPoint exclusively for nothing other than teaching how to use a proc. And so here we are, right? Let alone the first one doing it. It's going to be a 25 slider, but we're going to talk about how to use Proc Arima. And um, there's some value to doing it. It can do some interesting stuff that is difficult, maybe impossible to do in the time series forecasting system. But I also do think that as we kind of work through this proc, it will give us an even greater appreciation for how efficient that time series forecasting system can be. So Proc Arima, more generally, it's going to give us more flexibility, as we might imagine, but that's going to come at a cost. That cost is it's going to be more difficult to use, particularly if we want to kind of like create and compare lots of different models. As like a resource or a citation, a lot of this stuff just comes from the SAS help files, and then there's a link to Proc Arima in the SAS help files. So a lot of our procs have kind of had one main step, right? Proc Reg, for example, Proc Logistic, for example, they really just have that model step. However, Proc Arima has sort of three critical steps to it. So these are going to be like three different lines in our Proc Arima code. First is the identify step. So the identify step is going to specify what our dependent variable is, right? It's going to specify our y. It's going to specify which difference operators that we want to apply to it. And in return, it's going to give us the SAC and the SPAC, right? Which we could use for things like assessing stationarity, and maybe even more importantly, we could use for trying to determine what model we think we should fit. Once we've determined what model we think we should fit, we could then use the estimate statement. And so the estimate statement will actually fit a specified model. And as part of that process, it'll give us the LBOC scores, right, which we know are one of the more important things to look at. And then, right, if we want to see how well that model works, if we want to do some reliability assessment, we can use the forecast statement, which will provide us with forecasts. Now, I should start by saying this, right? One of the advantages of the time series forecasting system. Any pre-differencing transformation, like a log or a square root, must be done in a data step previous to running Proc Arima. We must also keep in mind that all of the output that you get, right, in particular forecasts in prediction intervals, will also be in terms of those logs or square roots. So you have to remember to reverse them before providing them to anyone for use or utility. So here's the identify step, right? So identify step reads, right, identify var equals y. So that would be if I just wanted to use the y as it is. If I wanted to do y as the first regular differencing, I would do y parenthesis 1. Now notice, right? Notice you might think the second regular difference is y parenthesis 2. That's not the case. It's 1 comma 1. It's basically saying, right, do that simple difference and do it again. If we think back to the backshift operator, right, that's basically saying do a 1 minus b to the power 1 times a 1 minus b to the power 1, right, which we know is how you would properly express that. If you instead you did y parenthesis 2, that's basically going to do y sub t minus 2 is how SAS would interpret that. Okay. If I wanted to do the first regular times the first seasonal difference, that would be y 1 comma 12, right? Again, if you're thinking of this in terms of backshift operators, that's going to be 1 minus b to the power 1 times 1 minus b to the power 12. Right, so knowing that backshift operator actually is pretty helpful, isn't it? When I run this code, what will I get? I'll get diagnostic information such as the SAC and the SPAC. I'll also get some other things which are occasionally used in time series analysis, things that such as the unit root test. We can control how far out the SAC and the SPAC go using the end lag, number of lag equals options, right? So I can go out 12, 24, 36, 48, right? If I want to look at some long-term seasonality. Next comes, right? So I do that. I figure out my appropriate differencing. Look at the SAC and the SPAC, figure out what my model is, and now I want to actually fit it. So I fit it with the estimate step. If I want an autoregressive model of order 6, which would include all six parameters, right? So the way that the time series forecasting system would do it, I would write estimate P equals 6. If I wanted an autoregressive model that only had parameters for times 2, 4, and 6, I could write P equals parenthesis 2, 4, 6. If I wanted to specify an autoregressive model that only had the 6th order term, that would be P equals parenthesis 6, right? So that's the way that notation works. If I want to estimate a moving average model of order 4 with all terms, right, I use Q instead of P. So I would do estimate Q equals 4. I can, of course, combine P and Q to build a mixed model. So if I wanted a moving average model of order 2 and an autoregressive model of order 3, I would write estimate P equals 3, Q equals 2. If I want to specify a model that has a first order non-seasonal moving average model and a first order seasonal moving average model, I can do estimate Q equals 1 in parentheses and 12 in parentheses. And that's going to do, again, just like we saw in the backshift operator, it's going to sort of set up these two different polynomials and then ultimately multiply them by each other. The options for the estimate statement, you could do print all, which will give you a lot of information. You could do no constant if you wanted to remove a non-significant intercept. And then you could do plot to get a number of diagnostic plots. You can suppress information with the no print option. On the identify statement, right? Because every time you're running your estimate, you're going to keep getting like all that spam from the identify statement. You're going to keep getting your SAC and your SPAC, for example, and you may no longer be interested in that. So you can suppress that by adding the no print option. Now, one really nice thing that you get from Proc Arima, maybe one of the best things about Proc Arima, that you do not get from the time series forecasting system is correlation between estimators. So one thing that you'll see in your Proc Arima output is this correlation matrix, where it looks at the correlation between all your beta hats, or I guess in this case, theta hats and phi hats. This is kind of the time series analog of the collinearity that we had, or that we talked about back in 512. And so you're going to look at this correlation matrix, and you're going to see all the different correlations between all the different estimators. And ideally, you're going to want them to be less than 0.90. So any correlation that's more than 0.90 is troublesome and might mean that we want to go ahead and remove that estimator. The forecast step is pretty straightforward. If I wanted to forecast 12 time periods into the future, I would just do forecast lead equals 12. Man, I didn't put it in the slide, so I may or may not end up eating my tongue on this. But I believe if you wanted to hold out some observations, like if you wanted to hold out a year's worth of observations, I believe you would type back equals 12. And if I end up being wrong, I apologize. But of course, I cited the SAS help file, so we can look it up there in a pinch. You can output these forecasts into a data set if you wanted to, say, for example, like apply a reverse transformation to them using the out equals option. Right, and again, yeah, here I am. SAS will not undo those pre-differencing transformations, although thankfully it will reverse the differencing transformations, right? So maybe you take the log and then you do a bunch of differencing. Your forecasts will have reversed the differencing, but you'll still need to exponentiate them. All right, so here's some example code. Say we take the first regular and first seasonal difference. Say we decide that's what's necessary to get overall stationarity. Looking at the second SPAC, we determine that we want a second order moving average non-seasonal model and a first order autoregressive seasonal model. Here, I guess we're assuming monthly data. So, right, Proc Arima, data equals, identify step, var equals y, 1, 12. So that's the first regular difference and the first seasonal difference. Estimate, p equals parentheses 12. That gives just the seasonal component. And q equals 2 will give us the moving average components 1 and 2. And then I can forecast, right, 12 months into the future. So that's the basics of Proc Arima. We'll try to play around with it in some labs. But one thing I wanted to show, which is pretty cool, is how we could use Proc Arima to actually handle to complement the type of modeling we did in 512. In particular, how to deal with regression models that have dependency in their error terms. So this is kind of like going back to week 1, right? So in week 1, we were dealing with data sets like this. Imagine we have a linear regression model with 3 dummy variables, quarter 1, quarter 2, and quarter 3. Well, we could sort of, so again, our goal is going to be what? Our goal is, I'm going to show us how to use Proc Arima to fit this regression model, right? This is essentially like a 512 model. Y equals time, Q1, Q2, Q3. The problem is we're going to guess that there's dependency in the errors. So we're going to see how to use Proc Arima to fit that regression model in a way that we would normally do in 512, but to build an Arima model for the error terms, right? Which is like an intuitive idea, isn't it? Like if we think about it, like what do we need to build an Arima model? To build an Arima model, we need stationarity. Stationarity, the two pieces that we at least look for in the scatter plot is a common mean and a common variance. And we would expect residuals to satisfy both of those properties, right? So maybe the idea that we should be making explicit here is what's really happening. I'm fitting a 512 model. I'm extracting those residuals, and I'm fitting an Arima model to the residuals. I would expect the residuals to be stationary, so that shouldn't be an issue. And by fitting that Arima model, I'm taking care of any dependency that might exist in those residuals. So I do that in Proc Arima. The identify statement, I have to identify my X variables. So I identify those with the cross core term. So that cross-core term is basically just saying like these are the X variables I'm going to be working with. And in the estimate statement, I'm basically saying like these are my inputs. Right now I'm even being more explicit. I'm saying like these are the inputs into my model, right? Inputs as in independent variables. Time, Q1, Q2, and Q3. Yeah, so identify statement, cross-core allows us to read other variables into the proc. We could apply difference transformations to those if we need to, using the same syntax we do for Y. The estimate statement essentially fits a 512 regression model using whatever variables are in that input option. And the estimate statement will generate a SAC and a SPAC for the residuals. Right, this SAC and SPAC of the residuals is called the R-SAC, residual SAC, and R-SPAC, residuals SPAC. And we could use these R-SACs and R-SPACs to figure out what Arima model to fit to our residuals. Yeah. Or maybe even see if we even need to, right? It's possible we'll look at them and just see no spikes anywhere, which indicates that there are no dependency issues in our residuals. So once we've determined an error model, so for example, say we think a first order moving average non-seasonal and a first order seasonal model is appropriate, then we would just add the extra line Q equals parenthesis 1. So that's the first order non-seasonal model. And then parenthesis 4, that's the first order seasonal moving average model. Right, that is, right, any fitted Arima model using the P equals and Q equals option is automatically fit by SAS to the residuals. That's pretty cool. Now, a couple things when we're fitting these types of models, right? The forecast statement. Keep in mind when we're using independent variables to forecast future values for Y, we need to know the future values of the independent variables, right? So if I'm saying that like Y is a function of some X's and I wanna forecast Y like 8 time points into the future, I need to know what my X's are 8 points into the future. The easiest situation is where our independent variables are functions of time or seasonality, right? So the example we just did had time and quarterly dummy variables. I could fill those in for future values, right? That is, if my data set goes up to time point 60, just like in 512, I can add another line for 61 and just set Y to missing. Fill in the appropriate dummy variable as 1, the other ones as zeros. The other situation, right, is where I have some X variables that are not necessarily just functions of time. Right, so for example, like maybe I'm using like inflation rate as my X and unemployment rate as my Y. And so if I want to like predict 8 time points into the future for unemployment, I have to have some sort of value. I need to be able to feed a value in for inflation rate. That's not as straightforward, agreed? And that leads us to a more difficult, much more difficult type of model to deal with. That would be kind of maybe like the next level for this class, or in terms of what you're learning is, and that's called an Arima X model, right? It's an Arima model that has some X variables in it. And this is really just the tip of the iceberg, right? So there's so much stuff you can do with Proc Arima, right? These 25 slides seems like a lot, but I could probably do 100 in terms of like all the different things that we can do. Remember, SAS help files have lots of examples and other stuff. So if it's something that you're interested in digging deeper in, right, I encourage you to go back to that first slide and check out those SAS help files. Bye for now.